So we're going to talk about the solution to the walk-around quiz on projectile motion. This is the diagram that we're given. There is a flare that's going to be dropped from a moving airplane that's a certain height above the ground. And that flare is going to travel along this parabola to reach a target on the ground. And we're supposed to determine several things about the motion, including this angle theta, which is the angle of the line of sight, which is a straight line path from where the flare is released to where it hits the ground. And one of the main points of this problem is that the direction of the line of sight, which is determined by this angle theta, is different than the direction of launch of the projectile, which the diagram gives is determined by this angle I called beta. And beta, as you could see, is the angle between this direction, which is parallel to the ground. So I drew that parallel line by a dashed line. And this direction, which is parallel to the initial velocity. So beta would also equal, by intersecting lines, this angle on that side of the intersection must also equal this angle on that side of the intersection for those two directions. Okay, so that's the problem. I'm going to add one more thing to, well, a couple more things to the diagram. I'm going to make my positive directions, and this time, just because the motion is downward, I'm going to simplify my knowns. I'm going to make my positive y direction down. I'm going to make my positive x direction to the right. I'm going to add the other initial velocity is in this direction. The final velocity, by the time it hits the ground or just before it hits, will be tangent to this parabola. So it's going to be kind of traveling down and to the right in that direction. And because this is a free-falling projectile, the acceleration vector at all times is straight down towards the ground. Alright, so now I'm going to get my knowns. We are given a couple of these things. So delta y is given in the problem as 2,400 meters. I also know, because it's a projectile, that ay will be 9.8 meters per second squared, and ax will be 0 meters per second squared. To get my other knowns, I'm going to have to go back to my initial velocity, which I'm given the magnitude and direction of, and I'm going to have to make a vector diagram. So I'm going to make that separate from my picture so it's easy to see. So this hypotenuse represents the initial speed, vi. I'm going to find the y component and the x component. And when I add those together, this vector diagram shows that the total initial velocity will be down and to the right. And this is the angle beta that was given in the diagram. And by parallel lines and an intersecting line here, that angle beta is also equal to this angle here. So we know that beta is 30 degrees. We know the hypotenuse of this triangle, the initial speed, is 240 meters per second. So I'm going to use my trig definitions here. I know that sine of beta will be opposite over hypotenuse. That's VIY over VI. Therefore, VIY is VI sine of beta, which is 240 meters per second times the sine of 30 degrees, which is 120 meters per second. And cosine of beta, which is adjacent over hypotenuse, that will be VIX over VI. So therefore, VIX will be VI cosine beta, 240 meters per second. Cosine of 30 degrees, that comes out to be about 208 meters per second. Alright, so I've got 5 knowns. I'm going to add those other 2 up here to my table. Vix is 208 meters per second. VIY is 120 meters per second. I've got 5 knowns. That's all I need to do a projectile motion problem. And the strategy is going to be to use the 3 knowns here that I have on the y direction to solve for time. And once I know time, I can use that for both x and y. And I could find things like the x displacement, for example. Alright, we'll do that on the next page. So I need to find time. I could either use our quadratic position time equation and solve that using the quadratic formula. I'm actually going to do it a different way because later in the problem I'll need the final vertical velocity anyways, because that was part of the walk-around quiz. So I'm going to first find VFY, and then I'm going to use that once I know it to find time. So I'm going to use this DVAT formula that VFY squared is VIY squared plus 2AY delta y. I'm going to try to refocus this here. So VFY must be plus or minus square root VIY squared plus 2AY delta y. Alright, I'm going to choose the plus square root since I know that VFY is down and positive is down according to my number line that I picked. So I'm going to put in the numbers VIY, which is 120 meters per second, AY, and delta y. Put all that together. I find that VIY is 248, VFY is 248 meters per second. Alright, I'll need that later. Now I'm going to find the time. Again, I'm still doing the y variables. I'm going to do VFY is VIY plus AYT. And so T must be VFY minus VIY divided by AY. That's 248 meters per second minus 120 meters per second over 9.8 meters per second squared. That comes out to be about 13.1 seconds. So now I know the time. Okay, now I'm going to find what the problem asked for. It wanted to know that angle of the line of sight. So it wants to know this angle theta. And what I'm going to do is I'm going to find this delta x next. I already know delta y. And again, the biggest lesson from this whole problem is there's several different triangles in this problem. So there's a velocity triangle, a vector diagram that I made to find the components of the initial velocity. But there's also a totally different triangle here, which involves the distances, the distance of the line of sight, and then the delta x and delta y. So I'm going to call that a distance triangle. And this angle theta is completely different from this angle beta. And it's also different, as you can see, from the angle that the final velocity vector is going to make. So I have to make a distance triangle in this problem to find that angle theta. So that's what I'm going to do next. So first I'm going to find the delta x, which is Vix times t. And Vix was 208 meters per second. Time was 13.1 seconds. So delta x turns out to be 2,716 meters. All right, so there's another thing I found. I'm going to try to refocus this. Alright, now I'm going to redraw that distance triangle here from my original picture. This is the angle theta. This is delta y. This is delta x. So I can see that tangent of theta, which is opposite over adjacent, is equal to delta y over delta x. So theta must be the inverse tangent of delta y divided by delta x. Delta y was 2400 meters, delta x 2716 meters. When I do that, I get the angle of the line of sight, theta, to be 41 degrees. So that was one of the things the question asked for. Now, the other parts of the walk-around quiz asked you to find the final velocity vector, magnitude and direction, so that means I have to make a third triangle. This one, the hypotenuse will represent the final velocity, magnitude, and direction, and then the other two sides are its components. So this is VF, VFY, VFX, and I'm going to find its direction below the horizontal by this angle, which I'll call alpha, and that angle is also equal to this angle inside the triangle. Okay, so I know VFY, I already found that. VFX is just equal to VIX, since AX is 0. Alright, and so now I can find the angle alpha. I'll do that right here. The tangent of alpha is opposite, which is VFY, over adjacent, VFX. So alpha must be the inverse tangent of VFY, which I found to be 248 meters per second, over VFX, which is 208 meters per second. Alpha turns out to be 50 degrees, which should kind of make sense. I mean, that angle of the final velocity vector should be a greater angle than the line of sight angle, because this is coming down at a steeper angle compared to that line of sight. Now I'm going to find, so that's the direction of the final velocity vector. I need to find the length of this side of my triangle to find the magnitude of the final velocity vector. So I'll do that next. I'm going to use the Pythagorean theorem. VF must be the square root of VFX squared plus VFY squared. There's no plus or minus here because this is a magnitude, and which is always a positive number. Alright, so that's going to be square root of 208 meters per second squared plus 248 meters per second. Add that together, take the square root, and you'll find that VF, the final speed, is 323 meters per second. Alright, so we found all the things that the problem asked for. The only other thing to do is the graphs for this problem, and then we'll be done. So I'm going to do the x graphs on one page. Those are the easiest ones. I'm going to do the x position, the x velocity, the x acceleration versus time. This will be in meters. Time will be in seconds. Meters per second squared. The x acceleration is 0, and it's constant. So that's a really easy graph to make. It just looks like this. The x velocity is constant at 208 meters per second. That's another easy graph to make. And then the x position graph must be linear. It must have a constant slope because the x velocity is constant. And so it'll start at x equals 0, and it will go to its final x position at the end of the problem, which is 13.1 seconds later. We said that would be 2,716 meters. So there's my x graphs. For the y graphs, remember, I got to make these consistent with my positive direction that I found on my picture. So be careful about that. I'll have y position, y velocity, y acceleration. All right. The acceleration graph is easy. I'll do the easiest one first. That's a constant acceleration. I made my downward direction positive, so that'll be a positive 9.8 meters per second squared constant acceleration. Vy has to start not at 0. The initial vertical velocity was 120 meters per second, and it increased to 248 meters per second. So this is a linear graph, but the y-intercept is not 0. Alright, and then the vertical position graph, it'll start at the origin. It'll be an increasing position because the object fell down, which is my positive direction. The slope of this graph should not be 0 at the origin. The slope should be whatever that initial vertical velocity was. So I'm going to draw a parabola. I know this is part of a parabola, which doesn't have a slope of 0 here. It has some positive slope, and it gets steeper and steeper. So I'll just sketch it something like that. And so I know that by the end of the problem, the y position was 2,400 meters. All right, that's supposed to be a parabola, a curve. Okay, so that's the solution to the walk-around quiz on projectile motion.